Record. All right. Logarithmic functions. Okay, so notice that it does start with log, just like what other function that we just studied? Logistic, right. So you can actually abbreviate. I'm using the white marker. I don't mean to do that. Here we go. You can actually abbreviate logarithmic function to just log function, right? It's acceptable to say log function, but when we say that, we mean logarithmic, not logistic. Now, I know y'all know what log functions are, because even though it was during a pandemic and it was maybe on Zoom for some of y'all, you had them in Algebra 2, I hope, right? Okay, good. So we could skip this section and just test tomorrow. If y'all are willing to come in on Saturday, that is. Okay, because everyone remembers what they did last year during the pandemic like it was yesterday. Or I should probably say everyone remembers yesterday like it was last year in the pandemic. Maybe that's a little more accurate. Oh yeah, okay, all right. All right, well, I'll reteach you. So what comes to mind when you hear the word log function or logarithm? Because a logarithm is the basis for a logarithmic function. Growing, good. It's not scary though, right? It doesn't scare you. Some form of graph. Well, that's very vague. I mean, that could apply to anything. But yeah, okay, if that's what comes to your mind. A piece of wood, there you go. Hang on. Cole said a piece of wood. Hang on, I'm getting used to it. A piece of wood. All right. Yeah. A new setup over there. But it doesn't scare anybody, no? Okay. Well, if it doesn't scare anybody in here, it's probably because you didn't really learn it well last year. Because if you had learned it well last year, it would probably scare you a little bit, or at least make you kind of feel sick to your stomach, like, oh, logs. Because usually when people hear log functions, they go, oh, gross, I hate logs. People love to hate logs. Okay, so y'all are at this level of understanding. You don't know them well enough to fear them. If you know them at the next level, that's when you kind of fear them or they make you disgusted. But if you know them at that next level, then you actually like them. Then you really enjoy them. Then you love them and you can't get enough of them. And that's where y'all are going to be. And I'll take you there. So what is a log? Well, most mathematics can be claimed to be discovered rather than invented. The only thing that we invent is kind of the structure to help make sense of the mathematics that's kind of the unwritten code of the universe. But logarithms themselves, they're kind of a man-made invention. And here's why. Back in the day, as people started getting curious, right, and the scientific revolution was happening, people started looking up at the heavens. Well, this was long before people started looking up at the heavens, you know, but once we started getting the equipment that was able to analyze it, we started like quantifying things that were in the heavens, right? Like the distance between stars. You want to measure that in feet? Let's do that, right? And convert it to millimeters. No. What happens when you're looking at distances astronomically? They're pretty what? Big, right? So as people started to look up to the heavens and try to quantify it so that they can put mathematical models to it so they could predict, right? Like, I wonder if that asteroid's going to hit us or not. Don't look up. Have you seen that movie on Netflix? It's pretty good. It's pretty entertaining. So they were doing that and numbers were getting astronomically large. But then you also had like Anton von Leeuwenhoek. Who was that guy? We interrupt this broadcast for a Happy Pencil song. Let's sing it to Cole. Nobody really knows what this class is all about. 1, 2, 3. Happy pencil to you. Happy pencil to you. Happy pencil, dear Cole. and Anton von Leeuwenhoek. Happy pencil to you. Way to go. I mean, National Trivia Day was Tuesday, but Cole knew that the inventor of the microscope was Anton von Leeuwenhoek. So when you start looking into a microscope, you're looking at distances that are not astronomically large, but what? Microscopically, good adverb, small. So what do you want to measure the width of a bacteria cell in miles? Yes. Yes. Miles and miles of bacteria. Sounds delicious. No, you measure them in what? Millimeters? Nanomillimeters? Super nanomillimeters? Okay, yeah. So what's happening when this comes about is numbers started getting too big to handle or too small to handle, right? So a Scottish mathematician named John Napier said, I have a solution. I have a solution. Let's invent the cell phone and then we'll all just be looking at our phones and none of that will matter anymore. We'll lose our imagination, we'll lose our creativity, and we'll just become like the people in Wall-E. Oh no, I fell out of my chair, help. No, that's not Napier's idea. He didn't even know about cell phones. He said, hey, I've got an idea. What if instead of looking at all of the number, right, we just look at part of the number. So for instance, if we were looking at the data the other day, like I said, hey, yesterday, 1 million people in the United States became infected with the coronavirus. It was like a record that we haven't had in a while, 1 million new cases. And that's when we were talking about reporting numbers to the proletariat, to the masses. They understand 1 million, right? But do you really think, come on, do you think they were really exactly like 1 million new cases? Like it's almost midnight and they only have like 999,999 cases. And like, come on, just one more. Come on, nice round number. Get infected. No. Perhaps on Monday, there was like 1 million, I'm making this up, 346,221. How is that for a statistic? You think the news anchors are going to report that? Yesterday, there was 1,346,002. People are like, what? What? People at home are like, drinking their Jack, what would they drink at home? Never mind, Daniel. Daniel, what would they be drinking at home? Daniel? No, the other Daniel? Jack, Daniels? Either one of you, Jack or Daniels? What would they be drinking at home? Yeah, you're gonna lose them when you hit the 3, right? And so what do? We just say, oh, it's about 1 million, right? And people come to know that it could be anywhere between 2 million, maybe just under 2 million, or conspiracy theorists would say, or closer to 0, give or take 1 million, right? That's kind of the same thing. If you're measuring the distance from Earth to Uranus, it's a big number. What, Luke? I'm sorry, little wine. What? Did you think of a joke? What was it? What? Oh, okay. That's a big number. So I don't know. Does anyone have Siri? Look it up, little wine. Ask Siri, how far is it from Earth to Uranus? Really, this class is a little bit different than Miss Lincoln's class. I hope you're okay with it. 2.557 billion. Wait, slow. 2.557. 2.5-57. Hashtag. No. Let's start over. Oh yeah, good. Kilometers. Thanks. 1.9743. Okay, 1.97. Hang on, my eraser's too big. Sorry, I got to fix that. 1 point what? What? Billion miles? Million? Billion? Miles. Miles, right. Yeah. Yeah, I live 2 miles away, which is why I always drive right through Uranus on my way home. Yeah, billion miles. Now that is that's kind of the idea right there. You know, you just found that on the World Wide Web. That's kind of the idea behind what Napier had in mind. He's like, you know what? 1.7943, if we wrote it as a decimal, 1.79, and then we just put the tag billion behind it, people will know what that means, right? So even Google right now is using Napier's notation, because what does that actually, and thank you for giving it to me in miles, not like British units, like little wind. Yeah. Okay. Is it time for tea yet? No, it's too early in the morning.
Leagues.
For what?
Leagues.
Leagues? Oh, leagues. Yes. Yeah. Leagues of, yeah. Fathoms. Leagues, fathoms.
Tea bags lined up in a row. How many tea bags?
Nice. Yeah. Or politicians end to end. Bananas for scale, right? Washing machines, all kinds of crazy units of measure. All right. Now, look, if we rewrote this 1.7943 billion miles, that would be 1, 794, 3, and then what? If I just wanted to write it as an actual number, 0, 0, 0, 0, 0. We're growing up here in America, not England. So when someone says, or anywhere else in the world, I should say, on planet Earth, right? We're culturally literate. So when someone tells you 1.7943 billion miles, you know that the number that they're trying to convey is actually this. But this is, you know, a lot of people don't quite know decimal places, right? And so if you put too many commas and stuff, they're going to be like, I don't know, is that bigger than 82 or what, you know? But when you tell them, they hear billion, right? Okay. Now, if this number is supposed to be equivalent to that, let me ask you this. Do you think for reals, that Uranus happens to actually be 1,794,300 convenient thousand miles away?
No, it's probably just that they rounded up to 4 decimal places.
Wait, what? 4? I'm looking at this, the 4 decimal places?
No, on the previous number.
0.000? Oh, well, now how about on this number? It would be to the what place, Brady? What place is that? No, 100,000s. 100,000s, or I'll just write like this. 100,000 place. Yeah. So yeah. So that's kind of what Napier was saying. He was like, you know what? The number is so big that the 10,000s place and below, it's kind of inconsequential, right? What's up to 99,000 miles, you know, when you're heading to Uranus, right? That's just like, I mean, if you're traveling there in a car, give or take an extra 99,000 miles, you know, that's just like an extra 5,000 years or so. It's nothing when you're going to almost 2 billion miles, right? What's 99,000 miles when you have 2 billion, right? I have $2 billion. Here's $99,000. Oh, I didn't feel it at all, right? When the number is so big, the smaller units of measure become increasingly consequential, right? Now, do we have another way that we can write this number other than with the verbal tag at the end, billion, which most people understand? Like if you were to write this number in your science class. Yeah. We could write this as, whoa, easy there. 1 point, again, right? 7943. We would say times 10 to the what? Yeah, you have to go like, here's the decimal. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. Would it be to the ninth or negative ninth? Ninth, right? Because you got to make this number, which is closer than my house, you got to make it bigger, right? Miles. Well, guess what a log is? Guess what Napier's idea was? Scientific notation. That was Napier's idea. He's like, this part here is really, it's got like the genetic DNA. They called this the mantissa back in the day. You don't need to know that, but that gives you kind of like the level of accuracy that we need. And then after that, this is just called the power of 10, right? So if we start comparing things that are all billions of miles away, and we all are on the same base, then we can just compare these numbers, right? So that's what logs are. Logs give us a way to talk about really, really huge numbers, as long as we can agree on a base. And this is base 10. Scientific notation is based on base 10. But we don't have to use base 10. We can use base 5 or 7 or E if we want. But if we just look at the little piece there, it gives us enough information, okay? As long as we know what the base and the power is. Same thing if you're looking at really, really small numbers, right? Let's see, someone else look up what's the diameter of a single bacteria cell in America, not in England. Someone look it up. Anyone, if you got Siri. Or let's give a little wine another chance. Just look at what is the width, and you can look up any bacteria if you want. Look up yeah, how wide is a single bacteria cell? Yeah, an American bacteria cell. And a bacteria that doesn't speak with a funny accent.
A free bacteria cell.
Free bacteria cell. Because in America we're free. All right, I'm ready.
I don't know what unit this is.
What does it say?
It's like a weird U with an F. It's a micro.
Oh, micrometer. Yeah.
Micrometer.
Yeah. That's okay. No, it's that's okay. It's good. It's like a millionth of a meter. So what you got? 0.5 to the tooth?
No, it's
It's in between 0.5 and 2.
Oh yeah, because we don't have a specific cell. Between 0.5 and 2 micrometers. That's the mu. Yeah. Yeah. If you've ever used like mu torrent, you know what mu is, right? Yeah. Coefficient of friction as well. Very good. Yeah, mu. It's also what English speaking cows say, right? Mean. So let's go with the smallest. If it's 0.5, and we'll stick with meters, right? Instead of inches. Scientific notation does have kind of that advantage, right? What's the American unit that's the next level down from an inch? Well, no, because that gets back to metric. Nah, see, there is not one. We start talking about an eighth of an inch, a 16th of an inch. So scientific notation and metric units have that advantage. You have a meter, centimeter, millimeter, micrometer. Yeah, so that's a really small number, right? So let's write that number out let's write that in terms of meters, okay? A micro would be a millionth, right? So point, or let's put a 0 in 0.123. That's first one. That's the tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths, right? So would that be it? Yeah. Now that's not 5 micrometers, that's 0.5 micrometers. So if we do want to do 0.5 micrometers, we need to go over one more space and put another 5. So that would be, I guess, roughly the smallest. Yeah, because instead of 0.5 micrometers, we can call that 5, and then whatever the next unit down from micrometer is, which we don't know, right? I don't know. A nanometer, I guess that would be next. Yeah, extra micro. A netro, what? A micro. Is that what it is? Oh, I don't know. It was like, wow.
Yeah,
A nanometer. Yeah.
1,000th of a micrometer.
Ooh, so that's even smaller. Yeah, because that goes up by another factor of 1,000.
It's 1/1,000,000th of
1 billionth. Right. So anyway, when you start looking under a microscope, my point is things are microscopically small. We could write this in terms of meters if we wanted, because back then they didn't have the sophisticated level of metric, they didn't have all those prefixes, centi, micro. So they kind of stuck with their unit of measure and then, went with scientific notation, which we can still use, right? So this would be the same as if we just write it in scientific notation in terms of meters, 5 times 10, or we could say 5.0, right? You know that in your science class, you have like significant figures. Here we typically go 3 decimal places. 5.000 times 10 to the negative. And now we count, right? 1, 2, 3, 4, 5, 6, 7. So -7 meters. And again, that's probably not the best unit of measure to use, but yeah, we get the idea. So what's important here is that we know we're counting in base 10. If we start comparing things that are all to the -7th power of 10, now we could just start looking at cell sizes that are bigger and smaller based upon this part here. A 5 is bigger than a 4. Yeah, so on and so forth. That is the genesis. That is the origin of what first started out as John Napier came up with these ways to count. And it was very similar to, it was the precursor to log tables and what eventually became the slide rule. But because they look like carpals, right? Those slender little sticks. I don't even know how to use those sticks. I've never made a set or come across a set at a garage sale or anything. But they called those Napier's bones. Kind of a creepy thing, but it's because they look like carpals, right? And here's John Napier today. Okay. Those are also known as Napier's bones. Okay. But these look like long, creepy, long wooden fingers. So that's why they call them Napier's bones. But these are the precursors to what eventually became, and others built upon his idea. Just like in all in math, it's a human endeavor, right? And it kind of gives us today what we commonly now call a logarithm. So a logarithm is nothing more than a systematic way that allows us to talk about big numbers or small numbers or medium-sized numbers. Now we can apply them to regular-sized numbers that are all powers of a common base. Scientific notation chooses base 10. Okay. Now there is an actual specific definition of a log, and I'll call it log instead of logarithm because it's fewer syllables. So what exactly is a log? Here we go. A log is simply an exponent. Reread. A log is simply an exponent. Oh, okay. So in the scientific notation example, the log is this number here. The log is this number here. We're not looking at the mantissa. We're looking at the relative size of base 10, okay? So the log is simply an exponent. What's another name for a log? An exponent. What's a synonym for an exponent? A log. Good. It's an exponent, but it's a special exponent, right? Like Rob Gronkowski is special. USAA. Have you seen those commercials? Oh, but I'm special. Yes, you are, Gronk. It's a special exponent. It is a special exponent to which one must raise a particular base, like 10, to achieve a particular result or a particular number. Okay, that's all a log is. It's the exponent that you have to raise a particular base, like base 10, or we'll use base e, to get a result. Okay. For example, we know that 2 to the 4th is 16, right? Raise your hand if you disagree. No one did, right? I didn't give you much time to think about it. But no one would have done it had I give you more time, because 2 to the 4th is 2 times 2 times 2 times 2, and that's 16. Okay. So we call 2 the base and 4 the exponent. We can then say that 4 is the unique exponent to which we must raise the base of 2 to achieve the desired result of 16. That's a fancy way to say it, right? Maybe that's the conversation you would have at tea, right? 4 is the special exponent to which we must raise the base of 2 to achieve the desired result of 16. Yeah, so 2 to the 4th is 16. Got it. So in that case, if 4 is the exponent, the special exponent, what would be the log? Let's come back over here. What is a log? A log is just that special exponent. Yeah. What is that special exponent? It's 4. So 4 is the log base 2. Yeah? 4 is the log base 2. Well, we can write that like this. In mathematics, the word is an equal sign, right? So 4 is the log base 2. We abbreviate logarithm log, and as a subscript, we put the base, and we call that base 2. Okay. Now there's one thing missing. The 16. The 16, the desired result, goes right here. This is our desired result. We call that the argument. The thing that we take the log of, or the desired result that we want, is called the argument. All right. And now we've set up an equivalent mathematical sentence, right? An equivalent mathematical sentence. In English, we have sentence structure, right? And you can say the same thing a different way, like, when I get sad, comma, I do math to cheer myself up, right? We can say that differently. I cheer myself up with mathematics when I get sad. It's the same thing. We just put the sentence in a different structure. These right here are the same sentence with a different structure. I was going to say this and these at the same time, and that comes out as this. We read this as 2 to the 4th equals 16, and we read this one from right to left, log base 2 of 16 is 4. Okay, that's how we read this. Let's write that in quotations. Log base 2 of 16 is 4. Log base 2 of 16 is 4, right? Log base 2 of 16 is 4. We take the log of a number. We take the log of a number, just like we take the square root of a number, f of x. It's its own function, and the argument is the inside part. Like the radicand is inside the square root function. So log base 2 of 16 equals 4. How can we say that differently? 2 to the 4th is 16. Okay. So let's write this side by side. Let's come up here and say log base 2 of 16 equals 4, or equivalently 2 to the 4th equals 16. They mean exactly the same thing. All right. So which one do you prefer? Probably the bottom one, because you have a lot more experience with it. But the top one has its benefits as well, because notice when we have a log, it equals 4. We're talking about just the exponent on the base as an indicator of the size of the number. We're not trifling ourselves with all the extra zeros that are going to come in there. Okay. So the benefit of a log is it chops the numbers down the size if they're really big, or it brings the smaller numbers up to size if they're too small to talk about. We can talk about the exponent as long as we agree on the base as an indicator of the relative size of a number. Now, if you remember from Algebra 2, you probably talked about ways to go back and forth between the two. And maybe your teacher taught you this. To go from a log function to an exponential function that's equivalent, maybe I've seen it taught like this, like the around the world thing. Have y'all seen that? Yeah. We call this the base of the log. We call that the base of the exponent. So it's the same number. So 2, go around the world, 2 to the 4th equals 16. That's a gimmick. So if you like to learn gimmicks, that's fine. It works. That's fine. But I would appreciate it if you just understand what's going on here.
I just thought it was just swap the 16 and the 4. I just thought it was do that.
And then what do you do with the log?
You just slide it away.
Slide it away where?
Yeah, you turn the log into a table.
You turn the log into the equal sign.
Okay, whatever. I don't want you to think about it like that anymore. I want you to think about it this way. These are equivalent. We call this the base. We call that the base. The log is an exponent, right? Never forget, at the basic level, a log is nothing more than a what? An exponent. What's the exponent? 4. What's the log? 4, right? This means is. The log is 4. The exponent is 4. 4 is the exponent. The base is 2. Your argument is your desired result, okay? Because your little slide away the log and switch works when you're going from this to this, but how do you remember how to go from exponential to log? In other words, if I told you 3 to the 4th equals 81, write that as a log equivalent right below it. Go. Now you're going to have to slide a log back in. And where do things go? Yeah. Good. 3 is the base. So log base 3 of 4 is 81, right? No, there's got to be some switcherooning going on, right? So the log is the exponent. So the log is the exponent is equals. So the log is, and then there's only one other place to put this. Your desired result over here is 80. 3 to the 4th power is what result? 81. We put our desired result behind the log. It's the argument. Those are equivalent, okay? And so again, the benefit is 81 is not a really big number. It's reasonably small, right? But if we start talking about, oh, but 81 is a power of 3, and we start talking about all powers of 3, and we all agree that we're referring to powers of 3, then if I just say 4 compared to 5, you know what we're talking about, right? Which one's bigger, 4 or 5? 5. So which one's bigger, 3 to the 4th or 5 to the 4th? I'm sorry, 3 to the 4th or 3 to the 5th? I'm an idiot. 3 to the 5th. Yeah, see, that's the idea behind logs. It's kind of brilliant if you think about it way back in the day, right? We know that there's some parts that that we really don't need to talk about, but now it's developed into its own function, and it turns out that if you want to make a number really, really big, really fast, exponentiate it, right? We talked about how fast exponents grow, but if you want to make a number grow small very, very quickly, take the log of it. It turns into a way to slow down growth, right?
So logs are basically like anti-exponents?
Yes, let's say that. Logs are the anti-exponents. And by anti here, we don't mean they're like categorically against them, right? Like they pick it down with exponents, right? We mean anti-heroes, right? Let's go ahead and say the inverses of, because what does an inverse function do? It undoes the work of the other function. Multiply by 5, you want to undo it, divide by 5. Add 7, want to undo it, subtract 7, right? Logs and exponents are inverses of each other. Not just logs are the inverses of exponents, but exponents are the inverses of logs. Exponents speed things up, logs slow things down. Okay. Now, logs have a lot of applications. You've probably seen them like in social sciences. Like, I don't know if it came up as an equation in like psychology textbook, but a lot of times when you're talking about like memory and knowledge and social interactions, you know, things grow at different rates. So like we're going to talk about Ebbinghaus. Remember Ebbinghaus from Guilford's class? If you had Guilford, the social science, Ebbinghaus's law of forgetfulness. And if you've forgotten what Ebbinghaus's law of forgetfulness is, it's because Ebbinghaus's law is in effect, right? That's a log. It's a log function. He came up with a formula. It's a log function. If you're in your science class and you think about acids and bases, right? Acids and bases, hydroxyl ions, hydroxide ions. What the pH scale, in other words, is what type of scale? It's a log scale. It's a log scale. Yeah. Water as it's absorbed, or light as it's absorbed in water, is a log scale. Okay, it's a log scale. All kinds of things. Has anyone in here ever been in an earthquake? Or felt an earthquake? I guess if there's an earthquake on the other side of Earth, technically we're on planet Earth and the Earth is quaking, but we're not feeling the shaking because it's bobblehead day, not bobblefoot day, right?
There's not enough force from the earthquake to reach everywhere.
The Richter scale. Y'all heard of that? Not the Coach Richter scale. That's the thing in her bathroom at home. Right. I guess. I don't know. I don't know if she keeps it in the bathroom. I've never been in her bathroom. She's out with COVID right now. Protocol. Yeah, so that sucks. The Richter scale measures the intensity of earthquakes. Yeah. Invented by a guy named Richter. I don't know if there's any relation. I should ask when she gets back. But a level 1 earthquake compared to a level 2 earthquake on the Richter scale, most people think, oh, a level 2 earthquake is how many times stronger than a level 1 earthquake? 2 times stronger, but that would be incorrect because it's a log scale, base 10, and 2 is the exponent and 1 is the exponent. A level 1 earthquake is really strength 10 to the first, or 10, and a level 2 earthquake is really 10 to the 2th, or 100. How many times stronger then is 100 from 10? 10 times stronger. Yeah. So there you go. Richter scale. There's a lot of applications of logs. All right. How are we doing on time? 5 minutes? It's Friday, right? We've been to Uranus and back. That's a long ways. Almost 2 billion miles, right? Yeah. I mean, there's not quite 5 miles. Oh, billions, right? Everyone knows what a log is now, right? And you know the historical context of why it exists and who's the originator of it? John Napier, right? John Napier. And he was from where? Earth. Not Uranus. No. He was Scottish. Yeah. So if you're ever on Jeopardy, in fact, I watch Jeopardy every day. I record it and then I watch it in the evenings because it comes on like at like 4:30 now. We have to be here. But anyway, there was a question a while back. And the answer was John Napier. And man, I got it. Felt smart. I finally got one. Yeah, finally got one. John Napier, I yelled at the TV set. And then one guy yelled in and he said, Einstein? And I'm like, no, you idiot. Right? You're like, how do you not know that? Like the one question you know the answer to, and one guy gets it wrong. You freaking, where do you live? on Uranus? Blew your head out of your planet. It's John Napier. Man, wow. Hey, sticking with the Uranus planet jokes, what do you get? Last thing for the day. What do you get when you eat beans with onions? Tear gas. All right, we're done. We're done. We'll pick up there. We'll actually start example 1 on Monday, but yeah, there you go.